So in this section, our goal is to analyze force on an object due to some liquid, and in this case we mainly look at water as our liquid. So the idea is if an object gets submerged in water, what kind of force is acting upon it. So we basically look at the force from water pressure that acts upon that object. So let's say you're in a pool. You know that as you go down deeper into the pool, the water pressure increases due to the weight of water above you. So how much deeper into the pool or into the liquid you are, the force changes. So let's go look at force from water pressure on a horizontal plate first. So let's say we got a horizontal plate submerged in water, and this is the surface of the water, and that plate is d units below the surface of the water. So we know force is equal to mass times acceleration. So, and we know that mass is just density times volume, and the acceleration due to gravity is just g. Now, what is the volume of the water? Well, it's basically just how much the area of the plate is, its length times width, and then the height is basically how deep it is underwater. So how much volume of water there is over this plate is really just the area of the plate times the depth. So again, the volume we're going to replace with just area of the plate times how much d units it is below water. Density, we use notation rho. So remember, rho just means density of water or whatever liquid you're dealing with. And then g, due to gravitational force, we'll just keep it the same. So ultimately, we have force is equal to rho, let's call it rho g dA. It's easy to remember that way, rho g dA. So for a horizontal plate submerged under water, if we know the density of water or whatever liquid it is, we know the density, we know the gravitational force, 9.8 meters per second squared, for example, if we're in the metric unit system, and how deep it is below the water and what the area of that piece is, that'll give us the force due to that water on that horizontal plate. So let's go put up some metric and US units to keep in mind. So in the metric units, we have force equals rho is 1,000 kilograms per meter cubic meter. In the metric unit system, g is 9.8 meters per second squared. The d and the a will have to be given to us. So we'll say it's 9,800 d times a newtons. We know the units in the metric system for force is newtons. And so in USA units, force will just be 62.5 dA because remember, the weight density of water is 62.5 pounds per cubic feet. So we're already given that as a weight, and we don't worry about the 9.8 seconds, which is the acceleration due to gravity. It's already incorporated in there. So it's basically 62.5 dA pounds as a force in US units and 9,800 dA newtons in the US metric units. And that's only, again, for a horizontal plate. Now let's go also quickly talk about pressure on the plate. So pressure on a plate is defined as force per unit area. So pressure is force per unit of area you're dealing with. And we know that force from here is rho g dA per unit of area. And it looks like we end up with rho g d. So basically the pressure depends on how deep down you are below the surface. So pressure at any point in a liquid is the same in all directions, and all we have to worry about is how deep below the water or the liquid we are. Let's go look at the units. So we just modify this a little bit. All I did was take out the area portion because it's just rho g d in each case. And the units for it, well, it's force per unit of area, so it's newtons per square meters, which is also defined as a Pascal, abbreviated PA. Or it's basically in US units, force, which is in pounds per unit of area, which is square feet. Now let's go look at a couple of basic examples with these ideas. Find the pressure at the bottom of a swimming pool 4 feet deep. So all we care about is how deep we are in the water. And pressure, remember, is rho g d, how deep you are in the water. Since we are in the US unit system dealing with feet, this part is just 62.5 times d. And they gave us that we're 4 feet deep, so all we got to do is plug in the 4 feet deep that we are underwater, and that gives us 250 pounds per square feet. So how much pressure there is at the bottom of a 4 feet deep pool is 250 pounds per every square feet. Next simple example, find the force exerted by water on a 2 meter by 3 meter flat plate that is 4 meters underwater. So before, in the previous example, I was looking at finding pressure, so I just thought, okay, rho GD is all I have to worry about. In this example, I'm supposed to find the force exerted by water on that plate. So force, remember, is rho GDA in the metric unit system, basically 9800 dA. So these are the same. So force is what I'm looking for. So rho GDA or 9800 dA, again, because I'm in the metric unit system. Now this flat plate has an area, and it also is so many meters deep underwater. It is 4 meters deep underwater, so 4 for the distance underwater. And what is the area of that plate? Well, if it's a plate that's 2 meters by 3 meters, all I have to do is length times width to get the area. So 2 times 3 meters. And that gives me 235,200 newtons. I was looking for a force. So both of these simple examples, because all we're dealing with is a flat plate submerged in water. Pressure on it, simply rho GD. Force on it, rho GDA. What I need is the distance below the water and the area of the flat plate that I'm looking at. Things get a little bit more interesting when it's no longer a flat plate underwater and you have a vertical plate. So let's go look at that case. So how do we find force against a vertical plate that's submerged in water? So since the pressure changes due to the depth, we divide the region into n subintervals, where the pressure is acting about the same over that small region or that small area. Then we add up the forces. So kind of the same idea that we've used for other things. You'll have a vertical plate submerged in water, and you focus on one piece of it and think of it as maybe a flat little plate where you have the pressure acting about the same in that region, because remember, pressure here will be less than pressure is here, and we know that force is basically just pressure times the area of that thing. Remember, let's go back up, that pressure is defined as force per unit of area, so force is really thought of as pressure times area, if we just multiply both sides by A. So since the force will depend on pressure times area, and pressure changes whether you're looking at a piece up here or down here, we cut it in small regions, and then we just add up the forces vertically. So how do we set up the whole thing? I'm going to give you a couple of steps. First thing, as before when we were dealing with force, you want to set up an appropriate axis. So you set up an x and a y axis for yourself with the picture given so that things don't get confusing. Number 2, you just do force, which is rho GDA. However, the rho GDA that you deal with is not as simple as the horizontal plate. The rho and the g are the same. The density of water is still the same. And the g acceleration due to gravity is still the same. The distance that you're focusing on varies because it depends on which piece you're looking at. Are you looking at this piece that's a distance d underwater, or at a higher piece that has a different distance. So the distance will be changing, and also the area. I mean, if I'm looking at a piece like this that's symmetrical, the area of each segment is the same. However, if I change the shape to something like that, then this area at the bottom will be different than the area of the top piece. So the things that will be changing that you have to pay attention to are the distance and the area. So this will lead us basically to an integral if we chop up and add up all the pieces. So when we chop up the pieces and let n go to infinity, as you may have imagined, it turns into an integral. So I can pull out the constant and put it in front of the integral. And d will basically be the distance of that piece from the surface of water. So if you're focusing on some general piece down here, what is the distance from the surface of the water? And your axes will help you figure that out. And then a is the area of that piece that you're focusing on. And the area of the piece will essentially be just length times width. And so the length you'll have to find out. Your width will be a little delta x. And also, from where to where are you chopping up that vertical plate? So from A to B are the other two question marks that you're going to have to find based on your axes. So the things that are variable here to pay attention to, that don't remain constant as before, are the distance of the piece below the water, or the surface of whatever liquid you're dealing with, the area of that piece that you're looking at, which is essentially just length times width, and then also from where to where are you making up those little slices. So the 4 pieces that I have in red here are the 4 pieces that you're going to have to determine based on your axes and the picture that's given to you. So let's go ahead and look at examples of dealing with this in the next video.